Another feature that SAM has is to calculate the effect of shading on the output of a PV system. Let's see how that works. First, let's create a new file. We will choose Photovoltaics and PV Watt System Model, and then we will choose Residential and click OK. Let's start at the Location and Resource tab on the left side. We'll put this system in Harrisburg, Pennsylvania. Next, let's go down to the PV Watt Solar Array tab and we'll make this system 5 kilowatts. We'll leave the tilt at 20 degrees and we will make the azimuth angle at a little east of south at 170 degrees. Remember that the azimuth angle in the PV Watts tab will use a convention of 0 degrees as north. Let's get a baseline of how much energy this system will produce before accounting for any potential shading. We'll go down to the green arrow and let the model run. Looking down at net annual energy in the lower left corner, we see that this system produced a total of 5,862 kilowatt hour per year. Now let's see what happens if the array experiences some shading. In this video, we will only be discussing shading that affects the entire array uniformly, not shading of modules within the array by neighboring modules. The shading models we'll show are only appropriate for shading that affects the entire array uniformly. There are several different ways where we can account for shading of the entire array using SAM. Let's go back to the PV Watt Solar Array tab. Underneath the azimuth entry we modified earlier is a button that says Edit Shading. This will bring up a new window where we can edit our shading profile for our entire array. At the very top, you will see 5 buttons for importing data from 3 common solar site assessment devices and software: PVSYST, the Solmetric Sun Eye, and the Solar Pathfinder. Each of these buttons will open up a file browser and let you load in the appropriate data file. Beneath those buttons, we see a variety of checkboxes representing each of the different manual ways we can account for shading. At the top is hourly beam irradiance. Beneath that is month by hour, then azimuth by altitude, and under that the sky diffuse shading factor. In order to use one of the shading models, we would select the checkbox beside its name and then enter the appropriate information, whether by importing data or modifying the information right inside SAM. The common feature of all of these methods is something called a shading factor. The shading factor is a number between 0 and 1 that represents the fraction of the radiation that is allowed to reach the entire array. As you'll see in a minute, most of the models on the Shading tab in SAM deal with the beam shading factor, or shading between an obstacle directly between the sun and the array. SAM will take this value between 0 and 1 and multiply that value by the incident normal radiation for the corresponding hour from the weather file. That's why a shading factor of 1 is no shading, because multiplying the incident normal radiation by 1 has no change on the value. The sky diffuse shading factor, on the other hand, is the shading factor that deals with diffuse radiation, or radiation that is bounced off clouds or dust in the atmosphere before arriving at the array. This value is adjusted in only one place in SAM. The sky diffuse shading factor is also a value between 0 and 1. This shading factor is multiplied by the incident sky diffuse radiation value for the corresponding hour from the weather file. SAM will not count having multiple shading models checked as an error, so make sure to check only the boxes you want at any one time. SAM assumes there is no shading at the array if no boxes are checked. As we switch between different models, we'll usually unclick the previous model before turning the next one on. Let's look at each of the shading models in turn. The top option is hourly beam irradiance shading factors. When you click this value, enabling the model, you will see a single button beneath a short description of what the model does. In short, you can enter a beam shading factor for every one of the 8,760 hours in a non-leap year. As was said before, a 0 indicates full shading of the array, and a 1 indicates full sun across the entire array. Values between 1 and 0 should be used when some portion of the interval between values is sun and some is shade. For instance, if the array is completely shaded before 9 a.m., half shaded by 9:30, and completely in the sun by 10, then the beam shading factor for the hour of 9 to 10 a.m. might be 0.5. Obviously, this would be an inexact estimate and does not account for string orientation. The hourly beam irradiance shading factors can be entered manually or imported from a spreadsheet or some other source. The time convention for the hourly beam irradiance model follows that of the typical meteorological year file. Hour 1 in this shading model is the hour ending at 1 a.m. on Monday, January 1st. The next shading model is month by hour. As you can see, we have a two-dimensional table with the months running down the left side and the hours of the day running across the top. Each of the cells in the table hold a beam shading factor. As before, a 0 equals full shading and a 1 equals no shading. This model will color code your entries for you, so times with full shading will be red, and as the shading decreases, the color coding moves closer to white. And as you saw, to modify the cells, you can either click the cell and type directly in it, select many cells and use the Apply to Selected Cells button at the top, or import the data from a properly formatted text file. Let's try an example using the month by hour model. We're going to consider conditions where there is full shading between 5 a.m. to 10 a.m. from October through March. In order to tell Sam about this shading, we go to 5 a.m. on January and drag the mouse over to 10 a.m. in January, then down to the March row. Then go up to our text box in the upper right and type a 0, and click Apply to Selected Cells. Next, we'll go up to 5 a.m. on October and select across to 10 a.m. and down to the bottom row for December, and again apply a 0 to our selected cells. We can see two blocks from October through March, 5 a.m. to 10 a.m. that are all red. A quick note. In Harrisburg, PA, the sun will not be above the horizon at 5 a.m. during the winter, so we could safely ignore that in our shading model, but it also doesn't matter that we've included it. Remember that without shading, our array produced 5,862 kilowatt hour per year. Now that we have our shading indicated and our month by hour model enabled, let's click OK in our shading model and the green arrow in the lower left to run Sam's production model. As you can see, the array's net annual energy goes down from 5,862 to 5,357 kilowatt hour, a 505 kilowatt hour difference, or around a 9% loss. Let's return to our shading options in the PV Watts Solar Array tab. Before we do anything else, let me uncheck my month by hour model. We can leave our shading data in there, because unless the model is checked, Sam will ignore it. The next option is Azimuth by altitude, which is the appropriate model to use when you have or want to use a set of beam shading factors based off of the position of the sun. Again, we're looking at a two-dimensional chart. Down the left side, we have the altitude angle of the sun, and across the top is the azimuth angle. That means that the shading factors we find in each cell are the shading factor for when the sun is at the azimuth angle and at that altitude. We can also change the number of rows and columns to match the data we have or want to use by entering new values in the boxes in the upper right and adjusting my column and row headings appropriately. There's more about that in Sam's help documents. As always, when dealing with solar software, make note of the conventions the software uses for azimuth angle. This is especially important here because the convention used for this changing model depends on which version of SAM you're using. The newer versions of SAM, like you can see here, will use the same convention that we saw with the PV Watts tab earlier. North is 0 degrees, south is 180 degrees, and so on, while older versions will have that flipped. The convention that's used will be included in the help file. It is also noted here above the chart. Our convention for altitude angle is the horizon at 0 degrees. It might be helpful to think of this chart as an upside-down representation of the sky. Each cell represents a particular patch of sky, with the top of the chart being the horizon. In order to indicate the same shading profile we used before on a sun path diagram between 5 a.m. and 10 a.m., October through March, we need to indicate shading for every location where the sun would be during those times. Let's do just that. We're going to skip over the exact steps, but all of our shading will be in the easterly part of the sky. Like before, in Harrisburg, PA, the sun won't be above the horizon during some of the time period that we're calling shaded, but it doesn't matter if we include that or not. The result is that we have a triangle of shading that hangs from the top of our chart. This is because the shading happens during the parts of the year where the sun is lower in the sky and only when the sun is in the east. As before, let's run our calculation after clicking OK to close this window and clicking the green arrow in the lower left. The result is 5,372 kilowatt hour, a reduction from our original unshaded model of 490 kilowatt hours, or again about 9%. This value is slightly different than we saw with our hourly by month model before, but well within the tolerances of the model. In practice, you have to have some basis for determining the azimuth and altitude of obstructions. The traditional method is to use a transit or an equivalent tool to find the altitude of an obstruction above the horizon and its distance from south at the site of the array. This information might be included on a sun path diagram or other record. Other tools and software might be able to deliver this data in this format, and there is a way to import data using this model. Next, let's look at the sky diffuse shading factor. This is a global value that's applied to all of the hours in a year, and it indicates the fraction of the sky that is obstructed. We'll run through a quick example using a sky diffuse shading factor of 0.5. This says that for the entire year, 1/2 of the diffuse radiation that would typically hit that array in that area would not make it to the array. We close the window, click the green arrow, and see a decrease in production from a completely unshaded array of 1,395 kilowatt hour, or almost 24%. The production that remains is made up of direct radiation. Last, a quick reminder that this is not the place to account for partial shading of an array, or shading of an array by itself. Let's quickly go back to the beginning, start a new project, and choose flat plate PV instead of PV watts as our model. This is a more advanced model and includes two separate ways to account for shading. First, under PV subarrays, we find the familiar Edit Shading button that we just explored, along with an additional model to account for monthly shading caused by soiling of the modules. You can have up to 4 subarrays, and each one can have its own shading and soiling profile. Above the subarrays tab on the left side is the Array tab, and this provides a way for the user to tell SAM that the array might shade itself during different parts of the year based on the distance between rows and other information. For more information on both of these components of the advanced model, please see the help file.